Hello, welcome to part 2 on the lecture about lambda calculus. Hopefully you've seen video 1 already if you're here. If not, please go watch that, even though right now it's uploading. By the time you get there, it will hopefully be uploaded. So last time what we did is we implemented the predecessor function, which basically counts backwards for a number except 0, just give you 0, right? So if you give it 5, it'll give you 4, and so on, right? It just goes backwards on a number. Very simple. But the implementation is not the most simple thing. So we did that, and now we could kind of figure out maybe how we could do the minus function, right? How do we subtract numbers? Alright, well, it's gonna be, you're gonna have the fact that we did it for addition maybe should be a little bit of a hint, but it won't be as easy as doing this, right, as minus 1. But to come up with it, you could still use the same idea, which is, well, let's say we want to do 5 minus 3. So in order to do that, we want to count, we actually want to count backwards 3 times from 5, right? We go like 5, right? We go 4, 3, 2, right? We counted backwards 3 times from 5, and we get 2, right? Hopefully you are not confused about this if you're watching this video. So how can we do that? Well, what we want to do, the idea is same as when we did addition, right? To do addition between two numbers, we want to add 1 to one of the numbers, the other number many times, right? To subtract A from B, we want to do minus 1 to A, B many times. So let's see, 5 minus 3, we can do minus 1 to 5, 3 times, and there you go. That is giving us 2. So that's exactly how we could do it, right? We have, all right, so what we want is 5 minus 3, right? And we put it in that order. So really what we want is A minus B, and to get it, we're gonna have to do this, B minus 1 A. That's exactly what we could put in our minus 1 function, right? Which takes 2 inputs, by the way, A and B, and we're doing A minus B, and so we can write just exactly that. B times, we do minus 1 to A, B minus 1 A. And now we check it out. We can test it. 17 minus 10. Okay, it's going to take a while because maximum overdrive, just give it a second. Yes, maximum overdrive. Oh, it's on. Oh, I know exactly why. Okay, so obviously we cannot use it the same way we use the plus sign. Pretty much everything is prefixed. So that's how we'd have to do it, right? It's a function, and it's taking the 17 as an input and then taking the 10 as an input. Addition, we can have addition be prefix, but I mean, it kind of already works this way, so it'll be the only one. Okay, it's going to be the only operator that we use in between the two arguments like that. And I could prove to you, because I was trying to figure out a while ago, how can I do multiplication? Let's say I want to do 3 times 2 this way, or 3 times 4, right? How can I do this? How can I, just because like the same way I have addition this way, how can I make multiplication work this way? And I'll tell you why we can't even do that. You just have to think about a simpler multiplication. 0 times anything, 0 times x. So what's going to happen, right? Well, you already know 0 is a function that takes 2 things and returns the second thing, right? And we're going to be applying that to the star and then to the x. And well, when you do that, it's just going to give you the x. So no matter what you define, infix multiplication to be, let's just define it to be, no matter what you define infix multiplication to be, it won't work, because something like 0 times 4 is just going to give me 4, which is totally wrong, right? Because that's what 0 is. It's really false, and false is a thing that takes 2 inputs, and it gives me the second one. So that was just a little side note here. Now we have subtraction. We could figure out how to do less than or greater than. Well, actually there's an easier way. Oh, actually we don't have everything yet, because we actually need a is0 function. We need a function to tell us if something is 0. And also they do tell you how to implement greater than, so it's not as hard. It wouldn't be as hard once you know how greater than works. But alright, the last thing we want to look at on this paper is this function right here, z, which tells us if a number is equal to 0 or not, right? So let's just write it down. Right. In my version, I'm not going to call it z. Because I can use pretty much any symbol except for a lambda symbol and a dot and parentheses to name variables. I'm going to call it equals 0 like that. And I'll just copy down the code. It says x dot x and then false. That f is actually a false, and then that weird symbol right here is actually, well, a not, right? And that's a logical symbol, the mathy logical symbol that they use for it. So, well, now all that's left to do is check if it works, right? Is 0 equals 0? Yes. Is 1 equals 0? No. Is anything else equal to 0? No. Right? And also remember, it's telling us 0 because 0 is actually the same as false. And so nothing really I can do about that. Yeah, is 19 equal to 0? Right. Is 20 equals 0? Is 21 equals 0? Oh, look at that. We don't know because 21 is not defined, right? 21 is meaningless, right, so far, because we don't have it defined. But if we did, it would tell us it's not, because it's not 0. Explanation on how it works real quick. Okay, well, x is going to be replaced with whatever number we're checking, right? And so what happens if it's 0? If it's 0, if it's 0, it's going to select not, right? Just worry about, for now, just look inside these parentheses, right? If it's 0, it selects not. And then this will be not, which will be applied to false. Not false is true. So it makes sense that this will give us true if x is 0. Now how about if it's not 0? If it's not 0, then, okay, well, we still look inside these parentheses, right? Because x only takes 2 inputs. So let's worry about what it does with these 2 inputs for now. So if it is some sort of number, it's going to apply the function false a bunch of times or some number of times to not. And then that's applied to false, which seems weird, right? But let's actually let me show you that this is not as weird as you think, that it makes more sense than you think, right? So let's just say x is like 3 or something, right? So if x is 3, we're gonna have this maybe like false, 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 3 times false that we apply to not, right? And then on the outside, we still have false, right? Because we didn't do anything with it. Now, look at this. This is actually, you can consider it to be kind of like one term, right? This is one whole term. And what does false do? It takes 2 things. Here's the first thing. It takes this. And here's the second thing. It takes 2 things and gives you the second thing. So it's going to select this, which is false, which is what it should give us if we give it any number other than 0. So there you go. That's how we could explain equal 0 function. All right. Now we definitely have enough to explain how we could do less than or greater than, or at least kind of try to derive it ourselves, right? How can we do less than or greater than of two numerical arguments? Okay, first I'm gonna specify what type of thing this is, and well, okay, I'm gonna just 3, 4. I'm just gonna separate some stuff here. Okay, because this is like natural number stuff, and this is all Boolean stuff. Alright, so this equals 0 function is going to be for the natural numbers. It takes a natural number and it tells us true or false, is it 0, so it returns a bool. Alright, now this one, greater than, less than, greater than or equal to, less than or equal to, they're all going to be under these, which actually, no, it's not going to be under these. It's going to be under a new category of function, which are going to be functions that take two natural numbers, and it gives us true or false, however we decide to compare them. Alright, so, well, first one we'll do is greater than or equal to, because it's already defined here. But we don't need to look at them. We don't need to look at that to see. Alright, we could derive it ourselves, right? So it takes two numbers, x and y, and whether x is greater than or y depends on if something equals 0. If what equals 0? I think it's y minus x. Let me see, right? Yeah, y minus x. No, x, yeah, y minus, nope, x minus y. X minus y. Alright, why does that make sense? Because, alright, let's think about if they're the same. If they're the same, then x minus y does equal 0, okay? So the equality part is definitely okay. How about if x is greater than 5? Alright, I don't know, like x is 5, y is 4, 5 minus 4 is 1, that's not 0. Right? So actually this is wrong. So actually it's y minus x. Right? So yeah, if x is 5 and y is 4, then we're actually doing the predecessor function to y x many times. We know that natural numbers don't go below 0. That's the definition of natural numbers, right? And if we do the predecessor function to 0, right, if we try to subtract 1 from 0, we get 0. So if x is greater than y, then the result of this minus yx is actually, yeah, this is y minus x, right? Yeah, so if y minus x is 0, that means that x was at least y or it was greater. So that means that this is true. X is greater than y. Should we test it? Absolutely. So is 4 greater than or equal to 3? True. Is 4 greater than or equal to 4? True. Is it greater than or equal to 5? No, it's not. I'm sure you can do your own test to be even more sure. But I'm sure enough to keep going. So that's greater than. The rest of them should be really easy. If you want, pause the video and try to figure them out. Please do. Alright, so less than or equal to, basically same thing. We should just flip the signs. So equals 0 and xy, right? Of course. Is 3 less than or equal to 4? Oh, well, we don't do it like that. No infix, right? Is 3 less than or equal to 4? True. Is it less than or equal to 3? True. Is it less than or equal to true? No. Okay. Next two would just be less than and greater than, right? Greater than. Super easy. We could, it just takes x and a y, and we just say that it's not the case that y is greater than or equal to x. That makes total sense, right? And with this one, it is pretty much flipping either the x and the y or flipping the symbol, which is what I'll do. And now we can test it. So 4 greater than equal 3, greater than equal 4, greater than equal 5, no. Okay, 3 greater than 2. I mean, is it less than 2? Is it less than 3? Is it less than 4? Okay, so our comparators work. Number 1 has been knocked off the list. Real quick, as a side note, I guess I want to talk about function composition because that's something really cool to know about. And if you saw the video, specifically the one that I recommended, then it would have showed you about this already. This is pretty much how I learned about it. It basically means that we could write our functions in simpler ways. Alright, so take a look at this. These functions in particular. I could write greater than actually in this way. Multiply, not exactly multiply, but compose, right? Compose not with greater than or equal to. Not quite. Actually, no, not in this case. Actually, I need a different composition function. But I guess I'll go ahead and write it. I'll put it in the section of these functions, which are some miscellaneous functions, which I don't really know how to classify, such as this one, ID, right? So I'll put this one in there, and I'll just name it this, just so we know. Even though it's the same as multiplication, it works the same way. Just so we know we're not doing multiplication, right? Just for clarity's sake. Same way we're doing the +1 function. We're defining a +1 function and a plus function, even though they're exactly the same. That's what I'll do here, right? So that at sign will be a star, and I'll show you when I'll use it. And then I'll call this one be at underscore. And this will be alright, well, this one's going to be it takes a function and it takes a function, it takes two functions, right? And it returns the first function applied to the second function applied to two arguments, because that's what that function does. That function takes two arguments, so we'll put them there. And so why did I do this? I guess because it lets you write functions shorter. So now let's just remember this, right? Look at the form that this has, and this actually is the same form as this. Hopefully I didn't mess it up, but let's try it out. All right, so we do the at underscore not greater than or equal to, right? If you notice, it really does have the same form, right? F is really the not, and then the G is this greater than or equal to. Anyway, let's test it out. That is greater than. So greater than is 5 greater than 4. No, 5 is greater than 4, but it's not telling me it is. Did I misspell something here? I think I did. Okay. Okay. Not yx. Strange. 5 is greater than 4. If anything, I might just not do that. 5 is... Oh, it's because I'm putting... Yeah, that makes sense. Yx, I'm flipping them. Yes, it's because I'm flipping them. So what I'll do is I'll just flip this one, and that will make it all okay. Okay. So now, yes, 5 is greater than or equal to 4. It's not greater than or equal to 5. It's not greater than or equal to 6. We'll do the same thing to this, and we'll just flip the thing. And, well, it's a way of writing functions. So, yes, 5 is less than 6. It's not less than 5. It's not less than 4. I just wanted to show you that we can do this. I think we can do it here too. Yeah, so look at this. We have equals 0, and then this, and then the x and the y. So maybe what we could do is x. Oh yeah. Compose the function equals 0 over the function minus. Alright. So we'll test that out real quick. That is less than or equal to. So 3 is less than or equal to 3. Is it less than or equal to 2? Is it less than or equal to 4? Okay. That works. How it could work with this one, I'm not entirely sure because the arguments are flipped. So I think I might have to define another function or something in order to abstract this one, but I don't think I'm going to do that because of the flipping of the arguments. I'm just going to leave this one as is, and we're going to move on to the next one. So next one would be defining positive and negative integers using pairs of natural numbers. Alright. That's easy. We can do it like this. I'll call this int. Well, actually, this is how we can construct an int. One of the ways, it's gonna take a boolean, and it's gonna take a natural number, and it's gonna give us an integer. So this is the function to do it with. It's called pause, and it takes a natural number and it creates a pair, right? Because that's what they're asking us to do. They're asking us to do it with pairs. A pair which consists of the value true, and then the second of that pair will be the n. Neg, right? How to construct a negative number will be well, pair takes false and takes n, and there you go. Already defined the, well, let's actually define some numbers. So I'll do that using JavaScript again. So this is how we'll do it. Alright, so this time it's going to be a number, and it's going to have a tick mark after it, and that will indicate that it's an integer because we already have numbers defined, so we're going to have to define the integers just a little slightly different. So I'll just do it like that, and this will be 10 maybe 9 positive numbers. Oh, we'll do 10. 9 positive numbers. Define them up here with all the rest of the numbers, and this is just something we have to do. It's not the prettiest thing, but it's just something we have to do. I might as well just do 20 since I'm generating them with code. Alright, so 20 positive numbers, and then 20 negative numbers. Oh, let me just change something right here. They should have a negative sign in the front. So 20 positive numbers, 20 negative numbers. Actually 21 because we're including 0. 22, right? 0, negative 0, positive 0, right? Alright. So yeah, we have all the natural numbers, right? Well, 20 natural numbers, 20 positive numbers, 20 negative numbers. Super cool. And there we did it. We defined a whole bunch of numbers. Now we can move on to number 3, which is define addition and subtraction of integers. So we'll do that. Uh, add, right? This time I'll call it add. It takes an A and a B. If you want, please pause the video. And for all of these, I don't have to keep repeating myself and saying that before every single question. You might as well just pause the whole video now, try every single question out, and then check your work afterwards. So anyways, I will move on. We want to think about it, right? Addition, right? You have to really know addition to be able to solve this. The first thing you should notice is that different things will happen if the signs are different, right? And that's actually the case for a lot of functions with integers, right? Multiplication, division, subtraction. Well, multiplication and division, they also have to do something if if the signs are different. So I already know I'm going to be using of this function quite a bit, a little bit at least, right? And it's going to be a function that takes two integers and it returns a boolean. And what does it do? It tells us if the signs are different, and I like to call it icy hot because it tells us if one is negative and one is positive. So it takes an A and a B, and then it tells us XOR, right? Well, I want to create even more functions, right? This one will take an integer and it will give us a natural number. We call it absolute value. Abs is a function, right? I'll do it this way first, right? It takes an int and it's going to give us the second of the int, right? Because we already know that that's how ints are defined, right? As pairs, and to get, and the first one is the where is it? Right here. The first one is the sign, right? True or false? Is it positive or negative? And the second is the actual natural number, the absolute value. So instead of this, we can just write SND, right? It's actually the same as the second function, but now called something that would make sense more to us now that we're working with integers. How about getting the sign? Well, we know it's just the first function, right? FST, and it's a boolean, right? But for our sakes in working with natural numbers, let's call it signum, which is the sign, right? We can signum definition, something that marks or represents. Okay, well, represents either positive or negative number, right? Signum equals first, right? So it tells us, is it a positive number or a negative number, right? Now we can use it here. So XOR, right? Meaning, you know what XOR does, right? If it only gives us true if they're different, right? XOR, true, false. Wow. And that's true. XOR, true, true. That's, however, false. Okay? So signum, the sign of A and the sign of B. Signum B. Alright, so that'll tell us if the signs are different. And now I guess we can add. So, by the way, we can do multi-line definitions, which is what I'm going to do for this one because it's kind of long, right? I'm just showing you right here when you first go in here. Yeah, you could have a multiple line definition as long as you indent after the first line. So yeah, that's what I'm going to do. So first I ask, do they have different signs? If they do, then you know what's really going to happen, right? It's going to be actually a subtraction of the bigger one minus a smaller one, where we keep the sign of the bigger one, right? Okay, and if it's not different signs, then we do something else, right? So remember, this icy hot AB will evaluate the true or false, and if it's true, it'll pick this pair of parentheses. If it's false, it'll select that pair of parentheses. So in the case where it's true, well, numbers are really pairs, right? So I'm going to need to make a pair of the sign that I get, right? The sign that I get and a pair consisting of the sign and the natural number, right? So that's what these two things are here, right? This is the first element of the pair, and this one will be the second element of the pair. And this whole parentheses, this whole thing is still what we get if we if the signs are different, right? And I guess it's simpler. It's simpler to do signs are the same first, so that's what we'll do first. It's still going to be a pair, so I'll go ahead and write pair. A pair consisting of the sign and the natural number we get. Now this will be really easy. The signs are the same, so I could just get the sign of any of them. So I'll get the sign of A. The sign of A, right? A pair consisting of the sign of A. So it's going to be, if A is positive, then positive. If B is negative, then negative. But they have the same sign, so it doesn't matter, right? And since they have the same sign, the addition is actually really easy. Just the addition of their absolute values, right? Abs A plus abs B. Alright, so that will handle them. I'm just going to put some random stuff in here. It doesn't matter what I put in here because I'm going to just test out that it works for same sign additions first before I continue, right? So let's add a couple things. 4 and integer 4 and integer 5, we should get 9. How about negative 4 and negative 5? We should get negative. I accidentally put two numbers with unlike signs, so I got that. But here we put the like signs. Negative 9, 0, 0. Get 0, of course. Negative 0, negative 0. Okay, let's move on to if they have different signs, right? So now, well, we could think about the sign, right? The sign depends on whichever one is bigger, right? So we ask which one is bigger. Is abs A bigger than abs B, right? Or is absolute value A bigger than absolute value of B? Then we take the sign of A. If not, we take the sign of B. Okay. Now that's the sign. Now how about what the result is if the signs are different, right? Well, it's actually going to be whatever the bigger one is minus whatever the smaller one is, right? So like if we do 2 minus 5, the bigger one is actually the 5 and the smaller one is actually the 2 if we're talking about the absolute values. But we take the sign of the bigger one, which is negative, right? Negative 5, right? So 2 minus 5 would be negative 3, right? We take the sign of the 5, which is a negative, but the natural number that we get is actually the bigger minus the smaller when we talk about the absolute values. So 5 minus 2, 3, okay? Hopefully you didn't need all that explanation, but I did it anyway. So what we do is we subtract the bigger one, which is the maximum, which I'll define that function right away, right? The maximum of abs A, abs B, subtracted by the minimum of abs A, abs B. Okay, so there we go. That is the subtraction. Now all we have to do is we have to just define max and min for natural numbers. That's not going to be a big problem. It's going to be under these functions that take two natural numbers and return yet another natural number. Which are mislabeled, right? Because it should have yet another nat in there. And yeah, okay, so here we go. Max equals, it takes an A and a B, and Well, if A is greater than B, then it'll give us A. Then if not, it'll give us B. And min, very simple. If it takes an A and a B, and if A is less than B, then it'll give us B, A. Then if not, it'll give us B. Let's go test them out real quick. So max of 3 and 4. It should give us 4. 4 and 3. Min 3 and 4. 4 and 3. Alright, looks like it works so far. I kind of didn't really mention it, but the video that I recommended does mention it. It has to do with writing functions cleaner. But I did show this fact earlier, but I didn't really say anything about it. It's kind of like, okay, here's the fact, right? Okay, so here we end in a B, and it ends in a B here. We could actually take away the B. Ends in a A here. We could actually take away the A. I don't really have a way to explain it. Oh wait, that doesn't work. No, because then that causes A and a B to be free variables. So never mind that. Okay, never mind. I was just go ahead and make fun of me. I was just about to say a bunch of nonsense. So moving on. Let's go ahead and test the addition function now. So let's add two things that don't have the same signs. 4 and -4, we get -0. That's kind of weird, but still okay. 4 minus 5, -1. Plus -3, minus 1. And let's do that stuff in reverse. -3 plus 4. And how about plus 2, plus 3? Okay, it works. It seems like it works pretty well. Don't think it'll go wrong anytime soon. Subtraction. Okay, I want to show you subtraction. Obviously, it's really easy. If you know how to add, you should know how to subtract. But before I do that, let me just show you how to write functions nicer. Call this one add to. So here's the thing that I want to make nicer about it. We can get rid of a lot of repetition here. So oh, music stopped. Let me see what music I'll put. Wow, I get so distracted. Let's see. I'll put. Oh, it's tough. Music. Let's see. It's mind design. Mind design is pretty good, I guess. See how long we've been going? 38 minutes. Okay. Lower that a bit. Okay, so yeah, we're in the middle of writing functions nicer. I actually keep two tabs open in case one of them freezes or something, which you'll see it will have the ability to freeze if we have some sort of typo or something. So yeah, we want to write it nicer. The thing that we keep writing over and over and over again is this. Look, abs A, abs B. Look how many times. A bunch of times. Signum A we write twice, but that's kind of okay, I guess. But we do want to we want to not write it so many times. So here's what we're going to do, right? It's going to have the same beginning as before, but now check this out. It's going to return a function that takes an A and a B. And actually, we're going to immediately invoke this function. And we're going to pass in stuff to it. We're going to pass in abs A and abs B. So now, maybe you can see what it does already is that it calls this function with the value of capital A being abs A and the value of B being abs B. So we can pretty much put all this same stuff in there, but now instead of writing abs A, look how much nicer this is gonna get. We could replace them all with capital A and capital B. It's just a way of making your code drier. Dry is a programming principle which you should probably follow. It just means don't repeat yourself. So if you have a bunch of code with a bunch of repeated stuff, then you kind of want to take out all that repetition. It makes your code better, nicer, and everything, of course. So let's test it out. Yep, definitely I do like how it looks a lot more now compared to how it was before. It's definitely shorter. You could spread it on like one line and see. I'll do that after I test it. So let's add a couple things, and seems to be working. Okay, it's not that easy to see. It doesn't look like that big of a difference. So I'll just show you real quick that one of them is a lot shorter. Place. I'm just gonna replace the new lines out. Okay, I think I misspelled that. There we go. I don't know. Oh, well, maybe that should not be in a regular expression. Oh, I forgot to put the G thingy. Yeah. \NG. Okay, so now it is one line. And let's do that to the other one, which is just the regular old add. And there you go. You could see one of them is a lot longer. Well, not a lot longer, a little bit longer. But as you start to write bigger and bigger functions, you're going to want to do that. I mean, any simplicity at all from what we have is going to help. So we might as well. We might as well make things as simple as possible. Alright, now subtraction. Super easy. Why don't I just first write this function called invert. It takes an int and it's going to return another int. Invert. It's just going to get the additive inverse of a number. So flipping a number. I could also call it times -1. Maybe that'll times -1. That inverts a number as well. And yeah, why not? I'll even use. I'll just call it inverts. I'll settle with that. So it takes a number, and what it wants to do is we want to have a whole new number where we flip the sign of the old number and have the absolute value of the old number as well. So alright, invert 3, we get -3, invert -3, we get 3. Subtract. It's a function that takes a and a b, and we just add a with the inverse of b. Invert b, and I don't think I need to prove to you that this will work. So we're just going to move on. Alright. So now what we want to do is division. Okay? So recursively, also recursion, yes. So yeah, I didn't go over recursion, so we're gonna have to dive into this paper yet just one more time. And so here it is, Y Combinator. I kind of have like no way of explaining it. It's kind of one of the most complicated things here. But the point is that it's gonna be what we're gonna use to do recursion. So how can it, here's basically an example of recursion being used. Here's the function r, is going to be used recursively, but we'll call it the triangular number factory. Right? What are triangular numbers? I think you know, maybe it's just a series of numbers 1, 3, 6, 10, 15, etc. It's the sum of the first n natural numbers. So the first one is 1, the second one is 1 plus 2, third one is 1 plus 3 plus 2, 1 plus 2 plus 3, and then the fourth one is 1 plus 2 plus 3 plus 4, which is giving us 10. And so how is it doing that? Well, we actually have to read the code real quick. Okay. Just give me a second to breathe. Yeah, okay, so basically when we apply the Y Combinator to some function r, the first argument, the first parameter of the function is going to become the function itself. Alright, it's super weird. Because in the lambda alright, hopefully you know what recursion is. But it's when a function just refers to itself. So in the lambda calculus, we don't have, the functions don't really have names. That's what lambda means, a function without a name. So we have to use the Y Combinator to do recursion. Yeah. So this little r is kind of the same as the big R, okay? So just trust it, okay? And then the n is the actual parameter that's going to take place. If you want, pause the video and read this stuff. Might be helpful, might not be. Okay, so the n is the actual parameter. So then we ask, is n 0? Is it 0? Then if it's 0, we return 0, right? That's what the 0 is there for. If not, we return this stuff in the parentheses, which is we add n, right? N plus, we add n to recurse, that's what the little r is, right? Recursion to, right? And then instead of n, we pass in p of n, which is predecessor of n, which is 1 less than n. So let me just rewrite this function in JavaScript real quick. Triangular, and it's a function that takes an n, right? Function triangular. Actually, it seems I have it defined here. Or I did define it before. Okay, so function triangular, it takes a number n. Oh, whoops. And then we ask, is n 0? If n equals 0, then we return 0, right? If not, we return n plus triangular n minus 1. Okay. So triangular number 3 should be 6, and then the fourth one should be 10, the next one should be 5, etc. So why I wrote that is just so that you could see that this function right here that they've written in the lambda calculus is really the same thing, except for this z function is the equal 0 function, s is the successor function, it's like the plus sign, and p is the subtraction by 1 function, it's a predecessor function. But this function cannot refer to itself because we don't have names in, we don't have we don't have names in the lambda calculus. So yeah, except that we are using the equal sign because it makes things a lot easier. So that's why we have the equal sign. It is cheating a little bit, but it helps. So we're gonna do it. I put classical music. Yeah, just something more calming. Hold on. A bit more soothing than that. Yeah, let's just pick one of these. Oh, best of Bach, okay. And I'll lower the volume a little bit. Okay. Okay, we're back. Oh yeah, we're here. Sub. Okay. So what you need to know is that when you apply this y combinator to some function, it's used to do recursion. Recursion on what? Some function that you define in this way where you're gonna use the recursion and you assume the first value, the first parameter is the function itself, the recursive call. I don't know. Please don't ask me to try to keep explaining this to you. I might just cry if I try. But all you have to do is just know how to use it, and that's good enough. So let's do that. We're gonna go ahead and define the y combinator, right? So go ahead in your code, in the miscellaneous functions section, because I don't really know how to classify it. General functions, whatever. Just put it in here, right? Y equals a lambda y dot lambda x dot y xx x dot y xx. Okay, there you go. That's the y combinator. What happens if we try? Oh my god, I can't believe I haven't really gone over this. It doesn't really matter, but I just feel like I should have gone over this way before, the fact that this exists. But the reason I haven't is because we don't really need to go over it to do our problems, right? And it's just the fact that there are functions that do not evaluate. There are functions that don't simplify, that don't reduce, and we call them divergent. And here's the simplest divergent function I know of. Here it is. Try to evaluate this by hand. Lambda x dot xx applied to lambda x dot xx. What happens when I use it? Look, nothing. Beta reduction in progress, but maximum call stack size exceeded. I mean, okay, so it should take you just 1 second of looking at this to realize what is going to happen, right? We could even rename these for clarity, right? So the y's here, every y is going to be replaced with a lambda x dot xx, and we get that, which is the same exact thing, which means it's just going to evaluate to itself forever and ever and ever, and it's never going to end. So this is what we call a divergent term. And that's actually what the y combinator is as well, a divergent one. It's divergent, I promise. The reason that's happening is because this xx was not, when you put no space between them, it's not two different x's. This is a free variable. It has nothing to do with this x here. So please put spaces between your variables. So there we go. Look, maximum call stack size exceeded because it's a divergent term, which is so much weirder, even more weird. Um, wow. And the fact that we're going to be using this in a useful way is very weird as well. So hopefully you find this intriguing and not boring or anything. Okay. So let's go ahead and do that. We have the Y Combinator. We're gonna go ahead and do division. Do it over here in our functions that take numbers and return another number, natural numbers. Okay, so just for clarity's sake, I'm gonna have a recursive version of it, and I'm gonna go by the convention that putting a percent sign after your function means that it's meant to be used with a Y Combinator. You know, it's like a recursive function that we are meant to be using with the Y Combinator. Okay, so division, I'll just say that it's Y division with a percent sign after it, and then AB. And of course, AB are the inputs that we take. So this one, well, the first thing is going to be the recursive call, so I'll just call it R, and then the things after that are the actual inputs, which will be A and B. Right, and hope you realize division is kind of recursive, right? That's how it is, right? We keep, to divide A by B, we keep subtracting A from B some number of times until we can't no longer, and then that number of times that we are able to do it, that is the result. So until we can't no longer, right? How do we know that we can no longer divide? We know when A is less than B. So we ask, is A less than B? If it's less than B, then the result is 0, right? It's like, well, we're doing integer division, so we're not getting any decimals. We're getting only integer back. So if we do 1 divided by 2, we get 0. 3 divided by 2, we get 1. 4 divided by 2, 2. 5 divided by 2, 2. 6 divided by 2, 3. So really it's giving us how many whole number of times can B go into A, right? Alright, so we ask, is A less than B? If it is, then 0. If not, we recurse. We do 1 plus the result, which is of, hey, we recurse, we do A, B. But this time A gets a little bit smaller, right? Instead of A, we do A minus B. So we basically subtracted B from A one time. And so this should probably work. And I'm going to go ahead and copy my code just in case something fails horribly. I'll make this one the light one just so I can tell the difference. Alright, so now let's test it out. Divide 20 by 5, or by 4, or by 5. And we get 4. Divide 20 by 4, we get 5. How about 19? What's 19 divided by 5? 3. We're doing 18, 17, 16. Oh, 1 divided by 5 is 0. 16, 15, and then once we reach 14, well, a whole number of times we can go twice. So that's division right there. Alright, where was it? It was right here. And while we're at it, while we're here, I guess I could do mod. If I need mod, I will implement it, but it's basically the same idea as division. So, oh, really important, really important. We do want to change something about the division function, because what if I try to divide something by 0? Let me just show you what happens if I try to divide something by 0. Okay. It's gonna time out. I'll tell you, it's not gonna throw a weird error. It's not gonna give us some weird garbage result. It's actually gonna time out. Why? Because right here in this step, when we do a minus b, right? So we're recursing, and then we do a minus b, where b is 0 because we're dividing by 0. And when we subtract by 0, it doesn't go down at all. So basically, a will never reach, it will never become less than b. It will never reach, it will never get less than what it is because b is 0. So it'll just cause my whole browser to crash, and that'll be what I test right now. So just so you don't do it. Don't do it at home. Okay, here we go. Beta reduction in progress. It's not even gonna say maximum call stack size exceeded. It is totally gonna crash the whole thing and never gonna recover from it. Poor thing. So that's why we don't want to do that in our division real quick. We just want to do a little safety check. We check if b is 0. If b is 0, then let's just return this right here. Say this error. Go ahead and exit the page. It'll never recover. So error div by 0. That'll be what I want the result to be if I try to do that. And now let's test it out. Divide 3 by 0. Perfect. I get this error right here. Error div by 0. And that's nice because we don't want to do that. Okay, so we did it. Now we can do the next thing, which was after division, which is now factorial. Yet another recursive function, and it doesn't specify that it's for integers or whatever, so I'm just going to go ahead and do it for natural numbers. It's a function that takes just one number and gives us one number. So I'll define it right here. Factorial. And factorial. I know it's going to be recursive, so let me take an n, and it's going to do y factorial recursive version over n, and then a factorial recursive version is gonna take an n, and it's gonna check, is the n equal to 1, or better yet, is it equal to 0? Is n equal to 0? If it is, then just give us 1. If not, give us n times, we do the recursion, right? Factorial. Oh, this one takes a r because recursion, right? It's factorial of n minus 1. So minus 1 n. And there we go. I think this should work. Factorial of 3 should give us 6. Factorial 4 should give us 24, but that's kind of big. I don't have 24 to find, so I'll just subtract 4 from that. It should be 20. There you go, I get 20. Real quick, I think this is something I wanted to do earlier, but I wasn't able to because I was just about to do nonsense, but this time I actually can do it. And okay, right here I have n here and I have n there. I could actually remove both of those and not have any n anywhere, and actually this will work. Check it out. See, factorial 4 minus 4 still gives us 20. Factorial 3 minus 4 should give us 2. Factorial 2 minus 4 should give us 0, because, you know, predecessor of 0, 0. Okay. So there you go. We did a factorial. Very nice. Very nice. I think I could do the same kind of thing for division as well. Oh, except that I have here the equal 0 b thing, so never mind. I can't do it anymore. Okay, let's continue. So now rational numbers as pairs of integers. Okay, rational numbers as pairs of integers. Alright, well that's gonna be easy. I'm gonna go ahead and make some space here. I'm gonna make some space here. I'm gonna go ahead and first specify what these functions do. Now I'm going to make some space. Okay. This is where we'll start talking about fractions. So fractions are going to take two integers in order to create a fractions, and it's going to give us back a fraction. This is for constructing fractions, and this will be the function to do it with, frac. Now it can't just be a pair. I agree, it can't just be a pair of the A and the B. That seems to be totally fine. I don't see a problem with that at all. But why don't we do things the pro way? We could really be doing things like a pro if we simplified the A and the B first. I think that'll be much better, simplifying the A and the B, because the next thing we're going to have to do is addition, subtraction, multiplication, division of it. And wouldn't it be so nice if every time we create a fraction, it simplifies immediately? That would actually be kind of cool. So that's what we're going to do. I mean, like, simplifying seems to be one of the key things that you do with fractions. So that's what we're going to do. It's not just going to be pairing the two together. It's going to be simplifying it all in one go. Okay, so the first thing, why don't I call it n for numerator, d for the denominator. But okay, this nd is going to be a pair of the new numerator and the new denominator, because I'm going to go ahead and simplify this numerator and denominator. And by simplify, I mean simplify their absolute values, because I mean the sign doesn't really matter when doing this simplification thing that I'm talking about, where we basically dividing the A and the B by the GCD, right? The greatest common divisors, right? So what do we want to simplify? Abs n, abs d. All right. All right. Yeah. And now in here, we can start actually making the real fraction. Okay, it's a pair of something and some other thing. Here's the thing. I know that it is the right proper convention to have the denominators of simplified fractions positive. So that's what I'm going to do. I'm going to have the denominator positive, right? Positive. And okay, just this nd is going to be natural numbers, the natural number numerator or denominator. So yeah, and the second of that is going to be the denominator, right? It's a pair, and the second of it is going to be the denominator, and the first of it is going to be, well, plus or minus whatever the numerator is, right? So the numerator would be first nd, right? Oh, this should be a nd. And what sign is it? Well, we just have to know if the signs are different. N and D, are the signs different there? If the signs are different, then negative. If not, positive. And there you go. Yeah. And I knew I was gonna have to use this function again, icy hot. So yeah, this should work. Now all that's left to be done is to define the simplify function. And by the way, simplify, I mean, it does take two natural numbers and it returns a pair of natural numbers. So I'm going to go ahead and mention that about it, that it does do that. So yeah. It will be over here with the other natural number functions. This right here. Okay. Simplify. And I'm pretty sure, does it have to be recursive? No, but GCD, the greatest common divisor, has to be recursive. So anyway, simplify. It takes an A and a B, and I'm gonna go just dry out GCD so I don't have to write it twice. And to that GCD. Right, and so anyways, simplify AB is going to be a pair consisting of, okay, by the way, GCD is, I'm talking about the GCD of A and B, and I'll have to define that in a second. So yeah, a pair consisting of dividing A by the GCD and dividing B by the GCD. This is getting a bit long. I'll go ahead and move it on to the next line. Okay, so yeah, a pair dividing A by the GCD and B by the GCD. Surely that will simplify it. Just I need to define GCD, the greatest common denominator. Alright, so this time I'm gonna okay, I know exactly what I'm gonna write, but how I know exactly what I'm gonna write is because GCD algorithm, because I know how to do the GCD algorithm, and just try to find a good explanation for it. Basically, it's like the GCD is the same. The GCD of two numbers is the same as the GCD of the smaller one, and the bigger one mod the smaller one. Or I don't even think it matters which one is the bigger and the smaller. It's just that the GCD of A and B is the GCD of A and A mod B. So yeah, or B and A mod B. Yeah, B. Yeah, and A mod B. Or A and B is. Just see what I write, and if you probably already know how to do it yourself. But what I realize now is that I do need mod, so I'm gonna go ahead and implement it. And since I do need to implement it, I'm going to change my recursive division function as well, right? So first I'll define mod A and B, and well, mod. So mod div mod, right? Div mod. Mod is the second thing out of div mod. Div mod will be a pair. I want to get the second of it. Div mod A B. There we go. The second after doing div mod to A B. And now I can do division as well like that, right? The first after doing div mod AB, and now I can define div mod. Div mod will be the one with the error, right? Div mod equals, it'll be recursive, so I'll say, well, first, okay, equals 0, then div slash mod by 0. And if it's not 0, then I will go ahead and go y div mod AB. Okay. Oh, and div mod is a function that takes A and a B. Alright. So now I can just take this and I'll just use the skeleton of it for div mod. Okay, so div mod, here it goes. Alright. Okay, Q will be the quotient, and I'll have it right here, right? So the base case is still when A is less than B, but instead when it's A is less than B, When a is less than b, we'll return this time a pair consisting of the first will be the div and the second will be mod, right? Div mod. Well, the div is q, right? Whatever q ends up being, the quotient. And then the mod will be, well, a, because at this point a is less than b, and a mod b is a is if a is less than b. So now the recursive part, well, okay, this stuff still happens. The only thing that's different is that instead of putting +1 here, we'll just put +1 here, q, and we'll add 1 to q. +1, q. Okay. And now we definitely want to test out everything before we test out some bigger functions. We definitely want to test out smaller functions. So let's test out mod and div. So div, once again, 15 divided by 5 should give us 3. How about mod? 15 mod 5 should give us 0. 14 mod 5, 4, 3, 11. Okay, they work. Simplify now. We're still in the middle of actually writing GCD, but now that we have mod, we can do it. So greatest common denominator of a and b, and it's still going to be recursive. It has a base case. Alright, so GCD with a percent sign after it of a and b. Okay. And so that's GCD, percent sign, and now this would be R, and then A, and then B. And basically, if B is 0, because it'll definitely become 0 eventually with the mod thing. If B is 0, then A is the GCD. If it's not 0, then the GCD is going to be the GCD of B, and then get the modulo of A and B. Alright, so yeah, this should work. Let's test it out. GCD 10 and 11. How about 6 and 9? Should be 3. 12 and 16 should be 4. 12 and 12 plus 12 should be 12. Oh well, this totally crashed because now I have 12 next to a 12, which means 12 to the power 12, which means that this is never going to recover, or it's just going to say maximum. Yeah, okay, it didn't crash completely to where I don't have my browser anymore, but it is going to say maximum call stack exceeded because I forgot to put a plus sign here. So now it should give me this 12, right? The GCD of 12 and 24 is 12. How about 24 and 12? Still 12. Okay. Another thing, the function composition can be written a little different or nicer actually, but we can remove this a and b here. Yeah. And we could just say it's YGCD. Yeah. Can I do that anywhere else? I think maybe I can. Doesn't seem like it. It seems like I could do this for positive and negative as well. Okay. Pause neg. Okay, I think, right, because I have an end here and I have an end there. I think just pair true. Yeah. Let's test it out. Positive. Let's make a positive number. Positive 13. Right. and well, no, let's actually add two positive numbers. Not positive, but just add two integers. Yeah. Okay. I just like making sure it works. And actually pretty sure I can do it for these two as well, the div mod AB, because it's the same as this at function. I could use this at function. So that's what I'll do real quick. So it's equal to at underscore first div mod. At underscore first div mod. So let's try it out. 12 divided by 4. Oh, we don't want to write that. We want to write it like this. 3, and then 12 mod 4 give us 0, of course. 3. Okay, that's really bad. Okay. Something. Okay. Well, thank testing. Testing is real good. Testing is good. Okay. I don't think that this was the problem. I think I actually just misspelled something. Div mod. Yeah, first. It should be the second, right? Because 12 divided by 4 is 3, not 12 mod 4. Okay, now it should work. 0. Okay. Okay, GCD works. Simplify, that should work too. Okay, and it's gonna be a pair. Okay, let's go ahead and simplify 6 and 9. It would divide them both by their GCD, giving 2 and 3. 16, 12. It obviously works. It works. 10 and 6. 10 and 7. There we go. The GCD would be 1 in this case. Okay. So we're still in the middle of simplifying the fraction, I think. Actually, no, now we can check. Okay, now we want to do some simplified fractions, right? Let's do like, and the next one is going to be adding, subtraction, multiplying, divide. So I'm going to go ahead and do some fractions that I will go ahead and add and subtract and divide and all that. So yeah, 1, 2. Hold on, let me fix my camera. I feel like the frame has been off a little bit. There you go. Okay, so 1/2. Well, 1/2 plus 1/2 is 1/1. How about 1/3? 1/3 times 2/3 is 2/9. And then let's see. Let's do a harder addition of fractions. 1/2 plus 1/3 is 5/6. And now I'll go ahead and define all these fractions. Oh. Yep. Okay. So 1/2. Well, I know 1/2 is really a fraction, which is -3 over -6. And maybe I want to do some negative fraction as well, right? -1/2 equals, I'll put it over here, -1/2 equals a fraction which is 4 over -8. Okay, and the point is I want to see that these fractions simplify to something good, to you know, to what's on the left side, right? 1/1 fraction, 2/2, 1/3 fraction, -1/3 fraction, 2/3 is 4/6 fraction, 2/9 is negative, and -4 over negative 18. And then 5 over 6 is a fraction, which is, I'll just say 5 over 6. Yeah. And, well, we want to see that something like 1/2 really is a simple fraction. Right now it's not. It's showing me the raw function of it. It's not what I want to see. Okay. What I want to see is that this tells me that it's the fraction 1/2. Oh, whoops, this is not pair. Okay, yeah, 1, 2, right? And so it's not telling me 1/2 right away. I think there's a reason for it. I think it's because, okay, basically, okay, here's something I should tell you about if I'm going to explain this. It's how does it know that 3 is the result of adding 1 to 2? How does it know? Right? Because what it does is it does the beta reduction, and then it has this weird lambda, which is like this, right? Like lambda fx dot fff x, but then it notices that 3 is the same, right? It's alpha equivalent to that lambda, and then it tells me, hey, well, you know, it's actually just 3. There's a simpler way of looking at it, so you don't have to hurt your eyes, Ronald. Here, it's actually just 3. It's not this lambda, it's 3. And so how it does that is that all of these functions that are defined already, it checks it for equality, right? And it says, hey, 3 is equal to that. So here it is, 3. But see, there has to be a limit on checking functions for equality because it reduces to the halting problem. And you can't, yeah, it's like if your functions are infinite and don't converge, then you can't check that function for equality with another function because it will never end. The check will never end. So I pretty much put a limit on how far it could check stuff. So that's why it's saying check out this error, possible divergent expression, index JS84. I think we can raise this limit a little bit. Let me see. Index JS84. Let me just see. I haven't tried doing this yet, but maybe it'll work. So let me see. All I have to do is change something here. Okay, so tread carefully. This 1,000. I can make it take 5 times longer. And I'm not sure if this code like gets saved. I don't think this code gets run. I might have to, or yeah, there's a warning symbol. So changes to this file were not saved to the file system, of course. Okay. But I think now, if I do this, I'm more likely to be able to see that there it is, 1/2. There it is. So okay, yep. Go inside the code, sources, index.js, change the 1,000 to I guess like 5,000, maybe even 10,000, just to be safe. And it will be able to tell you that this pair 1, 2 is equal to 1/2. And let's see, do I get any error with so now when I run this, I'm no longer getting a message that it's divergent. The only ones that it says are divergent is these two, division and percent sign. which is weird because I would feel like GCD is divergent because of the Y combinator, but whatever. Maybe there's a lot of things I don't understand. Okay, and also, right, if I make a pair of 2 and 9, it's gonna tell me that that is 2/9. So real nice. Yeah. The fractions are being simplified at creation. And that's going to be nicer for doing our work right here. So now what we want to do is addition, subtraction, multiplication of rationals, right? And, well, so these will be functions on the fractions, right? And they take a fraction, they take two fractions and return another fraction, right? So this one will be called add fracs, of course, and it's going to take off two fractions, right? And we want to think about splitting the numerator and denominator because that's going to make it a lot easier to work with, right? So right off the bat, it's going to be immediately executed function that's going to be numerator A, numerator B, denominator A, denominator B. Alright. And we'll go ahead and put those right on the outside. So numerator A, that'll be, well, the first A and the first B, right? Because a fraction is really a pair. So numerator is the first, denominator is the second. Second A, second B. Okay. And now what we want to do is just remember how to add fractions, right? We need to have a common denominator to be able to add them. So, well, we know it's going to be a fraction consisting of the denominator, right? To get a common denominator, the easiest way to do it is just multiplying the two denominators, right? So we can multiply, which I don't have defined yet for integers, but I will. It's very easy to find, right? dA and dB, denominator A and denominator B, and once we've multiplied the denominators, all that's left is to add the two numerators, right? Which by then the two numerators are going to be multiplying the numerator A with the denominator B with add that to the product of numerator B and denominator A. And that should be pretty much what, yeah, I feel like that's enough to add fractions. Now all we got to do is real simply just real quickly define mul, right? Multiplying and dividing. So mul is a function, takes two integers, and this time we want to ask again if the signs are different. ICAB, if the signs are different, then the result will be a negative. If not, it will be a positive. Positive, negative, what? We just multiply their absolute values. So abs A and abs B. And there you go. That's pretty much it. Division, super simple. Division between integers. We just divide that, right? That part. And pretty much both of these things stay the same. And I don't know how much of a point you see to it, but I guess you could dry this out, right? You could just have one function to generalize them both, multiply or divide, and it's going to take whatever operator it is, either multiplication or division, and the A and the B, and pretty much copy all this stuff over, and then the operator will be right here, right? Just zoom out a bit. And now this one can be defined by this. Multiply or divide. Well, which one is it? I'll tell you which one it is. It's multiplication. And now this one. Multiply or divide. Which one is it? It's division. And that's how that's going to work. We can go ahead and test it real quick. Multiply 3 and 3. How about the negative ones? Multiply -3, -3. And yeah, that seems to work. Now we can do multiplying the fractions, dividing the fractions, way simpler, right? But I guess since we already did adding the fractions, I can just subtract them just as easily, right? So to subtract them, I want to, okay. So I just add fracs, right? Add fracs, A with, I add A to, well now I actually want to split up this fraction. This fraction is the same as a pair. For now, yeah, it can be a pair because once you subtract it, it will end up being a simplified fraction anyway. So no need to simplify in the middle. That would be inefficient. So yeah, that part stays the same, and we can just we could simply flip the numerator. So invert first B. Alright, and I think that'll be it for subtracting a fraction. And before we multiply, let's go ahead and test out subtraction of fractions. Subtract, and we want to subtract 1/2. We want to subtract 1 over 1 from 1/2. It should give us -1/2. Okay, how about if we flip them around? 1 over 1 divided by 1 minus 1/2. Of course, if subtraction with fractions work, then addition should as well. And I'm convinced enough that it works. Maybe we'll do 1/2 plus 1/3 plus 2/3. 1/3, 2/3. And we get, oh, I didn't add them. I subtracted, so we get -1/3. So that's why I'll add them. Okay, and it does take a while. Add fracs. Maybe I should take the S away from this. Add frac. Yeah, I guess S should be there because plural, right? We have more than one fraction that we are adding. 1 over 1. Okay, excellent. Multiply. Super easy, right? Of course, you were so happy when you found out how to multiply fractions in grade school. I can't even tell you how happy you were, because it was just like multiplying them straight across. How easy is that? So easy. So it's a fraction consisting of multiplying the numerators and multiplying the denominators. Go ahead and put that on another line. First A, second, right, for denominator. The denominators. Yeah, so awesome, right? Weren't you so happy when you found out this was the way to do it? Division, that can be done very similarly, of course. We would just, instead here, we would just flip, you flip the second fraction, right? So instead we'll write second here and first there. And there you go, that is division of fractions. Let's take our tests down here. Okay. Alright. So yeah, let's divide some fractions. How about we divide or multiply this? Either way. Multiply 1/3 with 2/3 like I said I would to give me 2/9. Oh, another thing I never did is I never added 1/3 and 1 1/2 to get what 5/6. So might as wrong thing. I put add. This is gonna give me total garbage. So add fracs, and that will be 5/6. Okay. So yes, mult fracs, and how about we divide this time? Divide 2/9 by 1/3, which will actually be multiplying it by 3, which would actually be 2/3. The result of this should be, there we go, 2/3. So I'm pretty satisfied with the performance of my fraction functions. Now we can move on. It's been 1 hour and 40 minutes. Okay. So hopefully you are still here. Data structure to represent a list of numbers. Okay. So I'm not gonna lie, this is one where I had an old way of doing it, and it was kind of like very dirty and kind of like really smelly code. And then I guess I looked up another way of doing it and I used it. It was okay. I didn't really understand it though. And I guess then I read, which is of course it seems obvious, but there's obviously more than one way to do lists in Lambda calculus. And I really badly wanted to figure out my own way of doing it. So please, yeah, pause and try to figure out your own way if you want of doing lists. But yeah, I did figure out my own way. It took me a while. But the first way, both ways that I did it have to do with pairs. The old way I did it was like this, right? So like, well, let's say I want to have a list of like, I don't know, A, B, C, D. So that would be a pair consisting of A, consisting of a pair with B, and a pair with C, and a pair D, and at the end of that will be some value which is null, which I'll define later. And that is what helped me get the end of it. Somehow, using this simple representation, I was able to complete these questions. But then I tried it again, and okay, I had another video. By the time you're watching it, it's gone. I still have it at the time of making this video. It's basically I don't even want to say it because it's like embarrassing. It's kind of embarrassing because I think it kind of makes me look like a crazy person. But I have an 11-hour long video on Lambda calculus because I started off trying to, oh, the music is gone. No, I started off trying to explain. Oh crap, it started over. Oh well. And I guess so you don't have to listen to the same stuff over. I'll just pick something else. So yeah, okay, it's gonna redirect me here, but I'm just gonna go back to the music. Yeah, and so the thing about it is that you could pretty much, if you want to see that, you could watch me struggle and have a bunch of bugs. That's pretty much the reason it was so long. So yeah, you could struggle and watch me have a bunch of bugs here, but probably not. I'm probably gonna delete it. Actually, yeah, I might delete it right now because no one needs to see that, a bunch of bugs and all this stuff. I do try to implement it another way after I like look it up and then I do the rest of the stuff, but I figured out another way and this is gonna work fine too, right? Okay, so the whole issue here with thinking about how to do lists is that we need a way to define null, like null, the end of the list. And then using this definition of null, we need a way to tell us if the value is null or not, if the list is null. So pretty much this is what we need, right? Null, right, is some value that can be used as null, and then a function that tells us if the value or the list is null, right? So it takes a list and tells us if the list is null or not. Null is gonna let us know. I mean, like, if the list is null, then this is null will be true. Yeah. Okay, so the idea here, is that I'm gonna have okay, let me just write some stuff out. First, okay, each list is going to be a pair, a pair, right? And then the first is going to tell us, is it null, right? True or false? Is it null? And then the second element of the pair is going to be another pair consisting of the actual first element of the list, the head, right? The actual first element, right? That really, like, actually the first element of the list, okay? However that makes sense to you. And then the rest of the list. So tail list, right? And so, right, whatever this is, tail list is going to be yet again all this stuff, right? Which is a pair, right? Which tells it, the first tell us, is it null? And then, yeah. So, why don't we start off like this? It has to be a pair, right? Whether it or list or null, whatever we got, it's going to have to be a pair. Because how else are we supposed to check the first element for null? Has to be a pair, right? So pair. And, well, first thing is the marker. It tells us whether or not we have null. And, well, is null, right? Well, I'll just make it false, right? Yeah, false. It doesn't matter what I make this second element. It could be it doesn't matter. It doesn't matter what I name it. I'm just gonna call it ASDF or 0 or X or underscore, because I don't think it matters what I name it, because I'm only gonna be checking the front, right? Is null, right? All right. So, well, all I have to do is check the first element of the list, right? So, first list, right? And well, actually this should be equal to true because it is null, right? And now I want to check the first element of the list. So first, wow, actually, since this is the first, since it takes a list, I check the first element of the list. I can't believe it. Actually, null is the same as FST, right? It's the same as checking first. Yeah, and it's gonna evaluate the true or false because in this case it's gonna be only a true or false thing. And let me just go ahead and specify the data type of it. It takes a list and it returns a boolean. Null, it is a list. Alright, but since we're talking about how the lists are going to work, we should I should make this function, which is appending, right? Adding an element to the front of the list. How does it work? Oh, we're at 1 hour and 50 minutes. Okay, adding an element to the front of the list. All right. Well, here's the. It's a function, and it takes as input an element and a list. And okay, well here it goes, right? Pair. It creates a pair. Remember, because the first element tells us whether or not we have null or not. So in this case, since I'm adding something to the front of the list, the resulting list is obviously not going to be null. So I could just put it false right here, because it's not null. And then the second element of the list, it could be actually what the list is, which would be a pair consisting of the actual element of the list and then the list. Yeah, which is like the rest of the list. Alright. So, well, first we want to do some obvious checks, which is checking if null is equal to null. True. And that took a while. That looked like it took a while. I know why it's taking so long, by the way. If you see how it's saying 12 milliseconds and all this stuff, so it's actually taking really fast. It's being really fast. But what's taking so long? Look, 1, 2, 3, 4, 5. That's a lot. And it's the fact that we raised that limit there. When we raised this limit here, it made it so that it takes longer for it to check stuff. So I'm actually going to refresh this, and the limit should be gone by now, and it should take a little bit. It should be a bit faster. There you go, a lot faster, 10 times faster. So yeah, null is null. That's true. How about a list that we create? I'm gonna just create a list of. I'm just gonna call it A, B, C, D, E. Okay, so it's going to be a list of A. We append A to B and append B to C and append that to D. And append that to D, and then finally null at the end of that. And now we want to check if that's null, right? A, B, C, D. Oh, this is A, B, C, D, E, A, B, C, D, and it's not null, right? There's stuff inside this list. How about a list with just one element? Is that null? Nope, not even that is null. So great, I've defined a data structure to represent a list of numbers. How cool, how cool. But now, now we want to do extracting the first element from a list. Alright, let's do that. Extract first element from a list. By the way, this function, it takes an element or an expression, and it takes a list and it gives you a list. Just letting you know what that function does. Okay, now we want a function that takes a list. Actually, it takes a list, and it takes a number first, right? A natural number, and a list, and it gives us some expression, some term. So this function, wait, not yet. Actually, I got confused. I was thinking, oh, I should do element at. No, we just want the first element of the list. So this would be called head, right? The head of the list, the first element of the list. How can we do it? Pretty easy, actually. Takes the list, and it gets us the first after getting the second of the list, right? Because remember, the first of a list is going to be the indicator telling if it's null or not, right? So the second of the list is the actual list. And then the first of that is the actual element. And well, why don't we just test it out and see if I'm talking nonsense or not. I'll just keep this list defined here, A, B, C, D, and then it'll be a list of A and B and C and D and null, and there we go. What's the head of this list? Just A. Cool. Very nice. Very nice. That is the first element of the list. Alright, but now what it's asking us to do is define a function which counts. It's a recursive one. I don't see how to do it without recursion. Counts the number of elements in a list. Alright, so the type of it will be a function that takes a list and it returns a natural number. I'll just go ahead and call it length. It takes a list. Well, really, I could just say it's the y combinator applied to the recursive function that actually calculates the length of a list, and that function will be defined like this. Length equals function that takes the recursive call, which is itself, I guess, and it takes a list. And then how does it do it? Well, really easy. If the list is equal to null, then just 0. If not, then it's going to be 1 plus recurse, and we want to get everything but the head. So we want to have actually the tail of the list, which we don't have defined yet, but we will. Okay, tail list. So tail is a function that takes a list and it returns yet another list. So that's what this one will be. So list. Okay, tail. It's a function. It takes a list, and then, well, we can ask if the list is null, and we don't have to. I mean, if you don't want to do the tail on the list that doesn't is null, right? So hopefully you don't do that, right? But it's pretty similar to head, right? If you know head, you should pretty much figure out how to do tail, right? Which would be second list, right? Remember, the second of the list is gonna give us the actual stuff, right? Not the indicator telling us whether or not it's null, but the actual stuff, right? And the first one is going to be the head, the second is the actual list. Well, here's the second, the actual list. Right, the rest of the list, because the first is the first element of the actual list. I think you know what's going on. So let's get the length of A, B, C, D, which should be 4. And we get a frozen thing. Oh, look at this. I put tail here, but that doesn't make sense because that's the name of the function. It takes a list. So there you go. It gave us 4. What's the length of the list? Null. It should be 0. Alright, cool. I think, alright, it's been 2 hours. So I think what I'll do is the next question for last. Can you simulate a Turing machine using Lambda calculus? And so I'll see you in that video. I'll catch you next time. See you then.